Joining us now is another veteran of our teleconferences, Jack Schulze. Jack holds a chemical engineering degree from the University of Texas at Austin and is currently a member of the technical review and oversight team at the TCEQ. For those of you who've been around a while and thought Jack had retired, it's true. He once did retire, but he loved water so much, and much to the delight of his colleagues, he couldn't stay away. For you surface water folks out there, he's chuckling over here, I hope. Jack and his colleagues were responsible for the CT study, or concentration contact time template, and the monthly operational report spreadsheets used by surface water treatment plants here in Texas. He's currently assisting the drinking water protection team in their efforts to develop similar tools for groundwater plants, and he's here to explain how CT studies work for the groundwater. Jack, great to see you again.
Thank you for that introduction. Appreciate it. We're going to talk today about the groundwater CT studies. I just realized that there's nothing in your materials that address what CT studies are. Nobody's talked about it yet. So I thought before we move into the presentation, I'd talk a little bit about what CT studies are. CTs is the term used to describe the mathematical formula that you get when you multiply a disinfectant concentration C by the time that disinfectant is in contact with the pathogen before the water reaches the utility. So, I mean, the first customer. So C times T is CT. As long as CT that you achieve is greater than or equal to the CT required to control the pathogen that you're targeting, you will have met the disinfection requirements of the rule. So although it's a really simple complex, I thought because you guys aren't really all that familiar with the CT concept, because you've been dealing with groundwater and they haven't been dealing with CT, I thought we'd go ahead and talk about it so that y'all wouldn't get the DTs over CTs. I'm sorry. Let's go to the first slide and talk just kind of a general overview about what the CT study template is for groundwater systems. This is a one-page form that's used to evaluate the disinfection protocol at plants that are treating groundwater that is not under the direct influence of surface water. If your groundwater source is under the direct influence of surface water, you've got to meet treatment technique requirements for not only for viruses, but for Giardia and Cryptosporidium and Legionella and everything else that surface water treatment plants have to meet. So this is available, this spreadsheet that we have is available in a PDF format. It's available in Microsoft Word and in Microsoft Excel. It's going to be applicable at most plants that are treating groundwater not under the direct influence, using chlorine for disinfection, and have storage tanks that have both inlets and outlets. Now that we've talked in general about the presentation, let me show you the form real quickly. As you can see, this is a pretty simple form. It's only got 15 lines on it. It's not like the surface water CT study. And the reason that it can be so simple is that the form is really focused on a real small subset of the treatment universe. It's dealing with plants that are treating groundwater, we already talked, plants treating groundwater not under the influence. It's treating plants that are using free chlorine for their 4-log viral inactivation. They've got ground storage tanks or some other storage contact vessel. The inlet for the storage vessel and the outlet for the storage vessel both exist. That is, they don't use the same line to fill the tank as they do to draw water from it. Let's see, what else? Free chlorine. Oh, it's the ground storage capacity. The storage capacity at that facility has to be at least 30 gallons for every gallon per minute of flow through the plant. And it'll become kind of evident why that's the case as we get further into the form. But I wanted to remind you, as Joaquin pointed out, there are two reasons that this form is so short. And the first reason is that it was developed by a brilliant UT graduate. And the second reason was that it only covers this small world of treatment facilities. Fortunately, the small world of treatment facilities covers most groundwater systems. This is the top first 9 lines of the form. And I wanted to talk to you about and show you, although the form has 15 lines, there are only a very few pieces of information that you have to compile in order to do a CT study at a groundwater plant. Anything that's in yellow is data that you have to enter. Anything that's in light burnt orange is data that the treatment plant calculates, or values that the SWMOR calculate, or the groundwater CT template calculates for you. Let me go through each one of these lines individually so that you'll have some idea about how easy it is to pull the data together and what's going on when the template does its work. The first line is the total storage capacity of all the storage tanks at this facility, at this treatment site. And that includes the volume of water between the floor of the tank and the overflow elevation. Now, the overflow elevation is generally located below the roof of the tank, and since any water that you try to put in there is going to drain out, you don't get credit for that air, okay? The minimum water level or volume is the water level at which the level at which the water exists when the tank is as close to being empty as it is under normal conditions. And I'll give you some examples of what I'm talking about here in just a second. Maximum water level is basically the floor to the overflow. The actual minimum to max ratio is calculated by the template, and it just divides the top number by the bottom number and gives you a ratio. The maximum ratio that we allow is 0.5 for CT credit. The reason we don't allow more than 0.5 is that we don't want treatment plants to keep their storage tanks topped off. Wells are designed to run for prolonged periods of time to keep the well pump cool and reduce wear and tear on the pump motor. And so when the well kicks on, we want it to run for a long period of time. And so it's like we don't want you keeping the tank at the top 5% of the tank level. However, there are plants that don't have quite as much storage capacity as other facilities, and so they will draw their tank down lower during periods of peak consumption. So we give you credit for the lesser of those two values, and it puts the value in line 6, which is the allowable ratio. To calculate the allowable volume, we just multiply the maximum volume you can have in the tank by the allowable ratio, and it gives you the allowable volume. Baffling factor. Baffling factor is a term used to describe hydraulic short-circuiting, or quantify the hydraulic short-circuiting that occurs within a storage tank. When you calculate detention time, the easiest way to calculate it, the easiest way to think of it, is the volume of the tank divided by the flow rate of water through it. So you got a 1,000-gallon tank, you got a 10 gallon per minute flow, you'll get a 100-minute detention time. However, that detention time doesn't account for any short-circuiting that occurs within the storage tank as the water enters in a jet form and leaves as a suction. So in order to compensate for that, we have to include a baffling factor. The baffling factor times the allowable volume gives you the effective volume of that tank, okay? For CT credit, not for real world supplying water to people, but for CT credit. The bottom half of the slide shows you how let me give you an example. Let's go to the next slide and give you an example. What this facility has is two 42,000-gallon ground storage tanks. However, the tanks are 24 feet tall, but the overflow elevation is located at 22.5 feet, which means that the top 1.5 foot of the tank is not usable for storage capacity. Therefore, the tanks have an actual volume of 78,750. When the well pump kicks on, when the water level in the tank drops to 16 feet, the well pump will kick on. But during periods of peak demand, the service pumps are pumping out of that tank faster than the rate at which water fills the tank. So the water level continues to drop. When everything kind of balances out, input and output, when everything's kind of balanced out, the water level in that tank gets about 12 feet tall, 12 feet deep from the floor to the water level. At that point, the output with peak hours over, the output of the service pumps declines, they run less frequently, and so the water level in the storage tank starts to rise, okay?